I want you to try a little experiment with me right now. Look at the title of this deep dive on your screen. Or, look at a text message you sent earlier. What do you see?
I see words. I see a sentence.
Exactly. You see these distinct little islands of meaning. There's a word, then a nice clear space, then another word. It feels automatic. It feels obvious. But here's the hook for today. To a computer, that sentence is a lie.
A complete and total lie.
A computer doesn't see words. It doesn't see sentences. It sees a chaotic, unbroken ribbon of code, just a stream of characters, and figuring out where one word ends and the next begins.
It turns out that is a nightmare.
It's the classic iceberg problem of computer science. Looks simple on the surface, just, hit the space bar, right?
But underneath, there's massive complexity. And this isn't just academic trivia. This is the foundation of everything we do with AI. If a computer can't figure out where a word ends, it can't translate, it can't search.
It can't answer your question.
Not a chance. It fails at step 0.
So today we are doing a deep dive into the invisible infrastructure of reading. We're tackling text segmentation, and we're using Andre McKeeve's work on the subject as our map.
And McKeeve really lays out the groundwork here. The mission today is to explore how we teach machines to perform this low-level task of chopping up text, and why something as innocent-looking as a period can cause a multi-million-dollar algorithm to just fall over.
I have to be honest, when I first saw the topic, I thought, how hard can this be? We need a deep dive on spaces.
And that is the first trap, the space myth.
Okay, so walk me through this. If I'm a computer and I need to read a document, what is step 1?
Step 1 is what we call tokenization. That's the technical term for the process of identifying the boundaries of words or tokens in that stream of characters.
Right.
Now, for us English speakers or speakers of most European languages, we call these segmented languages. We're kind of spoiled because we explicitly use white space to separate words.
So rule number 1 seems pretty solid. If there's a space, split the word.
If only it were that simple. McKeeve makes a great point here right off the bat. Spaces are deceptive.
How so?
Just because there is a space doesn't mean there are two separate concepts. Take the city New York.
Okay, visually, new space, York. That looks like 2 tokens to me.
Visually, yes. But conceptually, it's one thing. It's a specific entity. If you treat new and York as separate tokens in a search engine, you might get results about something that's new in the city of York in England.
Ah, I see. That's a failure of segmentation. You've broken the meaning because you trusted the space.
You've completely broken it. And you have the opposite problem, too.
Where things are smashed together but are actually separate ideas, or...
Sort of. Look at the abbreviation UK for the United Kingdom.
U.K.
Right. It has periods inside it. No spaces. Ideally, that's one token representing one country. But a naive computer sees punctuation, the periods, and thinks, aha, punctuation usually means we stop.
And it chops UK into U and K.
And you've lost the country entirely.
So even in English, the quote-unquote easy language, the rules are already fuzzy. It sounds like every programmer must have tackled this differently, which sounds like a recipe for the internet breaking.
It would be chaos. That's why there have been these massive attempts to standardize this. You know, the Unicode Consortium, the people who basically govern text on computers, they have a guideline called Annex #29.
Sounds very official.
That sounds like a sci-fi treaty, doesn't it?
Yeah.
But it's actually just a set of rules for determining boundaries. And there was also an attempt called SRX Segmentation Rules Exchange.
And what does that do?
It's a standard file format. The idea is if I write a rule for splitting text, like keep UK together, I can send that rule file to you and your system understands it. It uses something called cascading regular expressions.
Cascading regular expressions? Okay, you have to translate that for me.
Imagine a waterfall of rules. The computer looks at a piece of text and checks rule number 1. Does it match? Great. If not, it falls down to rule number 2, and so on. It's a way of trying to impose some strict order on the messy chaos of human language.
But wait, it gets deeper. We're talking about splitting words. But looking at McKeeve's work, the complexity goes even further down, below the word.
Oh, yeah.
Into the letters themselves.
Yes. This is where we get into grapheme clusters.
This was my biggest, wait a minute, moment reading through this. I always assumed a letter is a letter. If I see a G on my screen, the computer sees a G. That's the atomic unit, right?
And 99% of the time, you're right. But in the world of Unicode, what you see as one letter might actually be a stack of multiple computer characters called Unicode points that are just glued together.
The example that really hit this home for me was the Hangul syllable from Korean.
Right. The text mentions the syllable gag. To a user, on the screen, it looks like one block, one character.
Sure.
But underlying that, it could be a cluster of 3 separate signals. One for the initial sound, one for the vowel, and one for the final sound.
So it's like a sandwich. The computer holds the bread, the meat, and the cheese separately, but it shows you a sandwich.
That's a perfect analogy. And it happens in European languages, too. Take the letter G with an umlaut, those 2 little dots on top.
Okay.
That can be encoded as one single character, a precomposed G with umlaut. Or it can be the letter G followed by a special combining character that basically tells the computer, hey, put dots on the previous guy.
Okay, but why does this matter to me? I mean, who cares how the sausage is made as long as I see the dots?
Well, developers care a lot. Imagine you write a program to reverse a string of text. Simple task, right?
Yeah.
If you treat that G with umlaut as 2 separate characters, the G and the dots,
Yeah.
and you just blindly reverse the order.
Oh no, you'd get the dots, then the G.
Exactly. The dots might end up floating over the wrong letter or just disappear because they have nothing to attach to. Or if you're counting characters for a tweet limit, does that G count as 1 letter or 2? If you don't understand grapheme cluster segmentation, your app is going to break.
It's like trying to move a house, but forgetting the roof is a separate piece from the walls. You might just leave the roof behind.
Precisely. You have to teach the computer to treat the cluster as the atomic unit, not the raw code points.
Okay, so we have spaces that lie and letters that are actually secret clusters. But the villain of the story, at least according to the breakdown, seems to be the most common punctuation mark of all.
The period.
The humble dot. Why is the period such a headache for computers?
Because it's the ultimate multitasker. It does way too many jobs. It marks the end of a sentence. It marks an abbreviation like Mr. or Doctor.
Yeah.
It's a decimal point in numbers.
And sometimes it does 2 jobs at once.
That's the doctor dilemma. This is a classic example in NLP, natural language processing. Listen to this sentence. He stopped to see Dr. White.
Okay, Dr. Gree is an abbreviation for doctor. The period is glue holding the title together. It's not the end of the sentence.
Correct. Now listen to this one. He stopped at Meadows. Dr. White Falcon was still open.
Oof. Okay. Meadows doctor. That's drive. And the period there is acting as the abbreviation glue and the stop sign for the sentence.
Yes. To a computer scanning left to right, Dr. Case looks identical in both cases. But in one, you keep reading. In the other, you stop.
So how do we solve this puzzle? Do we just give the computer a dictionary?
That's the first line of defense. It's called list lookup.
Yeah.
You basically feed the computer a massive list of known abbreviations. Mr., Mrs., KWG, Heaney, Eniba, you name it. If the computer sees a word with a period, it checks the list. If it's on the list, it keeps it together.
But you can't list every abbreviation in the world. People invent new ones every day.
Exactly. And some abbreviations are also real words. Sun with a period could be Sunday, or it could be the sun in the sky at the end of the sentence. In could be inches, or just the word in.
So the list method has holes.
Huge holes. So we add layer 2, heuristics, which is just a fancy word for guessing rules.
Educated guesses.
Exactly. For example, Mikiv notes that most single-word abbreviations don't have vowels. Think kg for kilogram, Mr. for Mr. So if the computer sees a short word, no vowels, followed by a period, it makes a guess, hey, this is probably an abbreviation.
Right. Or if it's a single capital letter, like in J.K. Rowling.
That's a huge clue.
There was a stat on this that I found really interesting. It said these guessing rules, these heuristics on their own, they only catch about 60% of abbreviations.
Which is not great. That's a D-.
Yeah.
But when you combine the guessing with the lists, your accuracy jumps to about 97%.
That feels much safer.
It's safe-ish. But that remaining 3%, that's where the funny translation errors happen. That's where a voice assistant starts reading a street name as doctor.
Speaking of confusing symbols, let's talk about the hyphen, because that's another one where a single symbol means 2 very different things.
Ah, the to split or not to split question.
You have the hyphen that just means, oops, I ran out of room on this line.
The end of line hyphen.
Yeah.
That's just an artifact of typesetting.
Yeah.
If you're processing a PDF or a scanned book, you have to find those and delete them to glue the word back together. Understand needs to become understand.
But then you have rock and roll, or 47.
True hyphens. Part of the word. If you delete those, you break the meaning. You don't want 47 as 2 separate tokens. You want the compound concept.
And then there are the ones in the gray area. The text mentions New York-based.
This is where it really depends on your goal. If you're building a system to recognize locations, what's called named entity recognition. You need to split New York-based, so you can identify New York as a place.
But if you were doing, say, a grammar check, you might want to treat it as one adjective.
Exactly. It seems like for every rule, there's an exception, and for every exception, there's a counter-exception.
And nothing resists logic quite like how we write numbers. I was surprised by how dangerous it is to mix up languages when you're dealing with numbers.
Oh, it's a disaster zone, the numerical chaos.
The example given was English versus French. In English, if I write 1, 2, 3, 456.78.
The comma separates thousands, the point is the decimal. Standard stuff.
Right. But in French,
It's often reversed or different. It could be written as 123 space 456, 78.
wait, they use a space for the thousand separator.
Often, yes. So now imagine you take an English tokenizer, a program built to look for spaces to split words, and you run it on French financial data.
It sees the space inside the number.
And it chops the number in half. 123,456 becomes two separate tokens, 123 and 456. You haven't just made a typo. You've destroyed the financial data.
That's a terrifying thought for anyone in international banking. You're not just misreading a word, you're fundamentally changing the value of an asset.
It highlights why pre-processing is so vital. You need specialized tools just to handle dates, times, and currency before you even let the standard text tools touch the document.
Okay, so far we've been complaining about how hard it is to process English and European languages. But the discussion takes a turn that makes English look like, well, child's play.
Non-segmented languages.
Specifically Chinese and Japanese. I asked earlier, it's just a space, right? But these languages, they don't use spaces between words.
No spaces at all. It's just a solid wall of characters.
The analogy used really helped me visualize this. It said, imagine if English had no spaces. The string together could be the word together,
Or it could be to get her.
to get her, exactly. Without spaces, ambiguity just skyrockets. In Chinese and Japanese, almost every character can be a word on its own, but they also combine to form compound words, so the computer has to decide, is this 3 separate one-character words or one 3-character word?
It's a huge puzzle.
So how do they solve it? If you can't look for a space, what do you look for?
One popular method is the longest match approach. The computer has a dictionary, it scans the string of characters, and it tries to find the longest possible chunk that matches a word in its dictionary.
That makes sense. It's safer to assume I wrote supermarket than supermarket.
Generally, yes. Japanese has an extra trick, though. It uses 3 different scripts mixed together: kanji, hiragana, and katakana.
Right. It's like having 3 alphabets in one sentence.
It actually helps. Often the script changes right at a word boundary. It's like if we switch from uppercase to lowercase every time we started a new word. It gives a visual clue.
But the text implies that even that isn't perfect.
No, it's only about 60% accurate as a rule.
Right.
So modern systems rely heavily on statistics, on n-grams.
We see this term a lot in AI. What does an n-gram actually do here?
It's basically calculating the probability of neighbors. The computer looks at millions of documents and learns, hey, character A and character B appear next to each other 99% of the time. They're probably glued together.
But character B and character C almost never stick together.
Exactly. That's probably a boundary. It's guessing based on the sheer volume of past experience.
It's amazing to think your phone is doing these massive statistical calculations just to figure out where a word ends so it can autocorrect you.
It's working incredibly hard to look effortless.
Okay, we've chopped the text into tokens. We've survived the grapheme clusters. Now we need to zoom out. We need to find the sentences.
SBD, sentence boundary disambiguation.
Again, I'm going to play the naive user here. Period. Space. Capital letter. That's a new sentence. Why do we need a complex acronym for this?
Because of that 6.5% error rate mentioned in the findings.
6.5%. That sounds low.
In the world of data, that's huge. If you rely strictly on the period space capital rule, you'll be wrong 6.5 times out of 100. In a standard novel, that's hundreds of mistakes. If you're Google Translate, that makes the text unreadable.
And this goes back to our friend the ambiguous period, I assume.
It does. But it also brings in the problem of proper names. The example used was the word black. It can be a name or a common word. Context is key.
The comparison was black described versus black umbrella.
Exactly. If the word black is followed by a verb like described, it's probably a person, a proper name. If it's followed by umbrella, it's an adjective.
So to find the end of the sentence, the computer basically has to understand the grammar of the next sentence.
Yes, that's the paradox. To split the sentences, you need to know the words. But to know the words, it helps to know where the sentences are. It's totally circular.
So how do they break the circle?
Machine learning. Instead of giving the computer rigid rules, you show it thousands of correct examples. You teach it to look at features. What's the word before the period? Is it capitalized? What's the word after? Is it a verb?
It learns the vibe of a sentence ending.
Essentially, yes. It learns that Mr. is almost never the end of the sentence, but ink often is.
Now, everything we've discussed so far assumes we're dealing with, well, civilized text, edited books, news articles, standard input.
But the internet is not civilized.
No, it is not. The source calls this the Wild West of text, non-standard input.
This is where the rules really fall apart.
First up, all cap PS.
The shouting text. This is a nightmare for segmentation because capitalization is one of our biggest clues. We use capitals to spot names and to spot the start of sentences. In all SAP-PS, that signal is gone.
So booish could be the president or a plant, US could be the country, or the word us.
And you lose the period space capital clue entirely because everything is a capital.
And then there's speech, text from audio recognition.
Right. Speech transcripts often have no punctuation, no periods, no commas, just a long run-on stream of words.
There was a mention of a system called CyberPUNC, which is a cool name.
Very cool name. It was designed to basically guess where the commas and periods should go in a transcript. It's inserting punctuation into a vacuum based on things like pauses and intonation.
And finally, the boss level, social media.
Microblogging, Twitter or ex-Facebook, text messages.
It seems like this created a whole new sublanguage.
It did. You have hashtags, emoticons, people skipping spaces because of character limits.
Or using you instead of you.
Exactly. A standard tokenizer looks at a colon and a parenthesis and thinks, okay, that's a colon, that's a parenthesis, 2 tokens. But on Twitter, that's a smiley face. It's 1 unit of meaning.
So they had to build entirely new tools like Tweet NLP just to handle this specific chaotic dialect.
Shows just how adaptable this field has to be. As humans change how we write, the foundational code has to evolve right along with it.
So let's bring this all back to the surface. We started by saying reading is easy.
And we learned that was a lie.
We've gone from the simple space, which isn't simple, to the hidden layers of grapheme clusters, the multitasking period, the chaos of numbers, and the wall of text in Japanese.
We've seen that what we think of as letters are often codes, and sentences are really just statistical guesses.
The big takeaway for me is that text segmentation is this invisible foundation. It's the concrete slab under the whole house of AI. We talk about ChatGPT writing poetry, but it can't do any of that if it can't figure out where the word poetry starts and ends.
Absolutely. It's a mix of rigid rules, massive lists of exceptions, and frankly, statistical gambling. It's messy, but it works.
It works most of the time, until you try to find a doctor on Meadows, doctor.
Touché.
So leave us with something to think about. We've spent this whole time talking about how hard it is to just find the structure of text.
Here's the thought that keeps me up at night. We have spent decades and billions of dollars just trying to get computers to agree on where a word starts and stops, just the physical boundaries, and we still have error rates, we still have confusion. If it is this incredibly difficult just to identify the container of the meaning, the word itself, imagine the complexity involved in actually understanding the meaning inside that container. If the computer struggles with Dr. Virtus versus Drive, imagine the hurdle of teaching it irony or sarcasm or love. We are building skyscrapers on a foundation that is still shifting.
That is both terrifying and fascinating. On that note, thank you for joining us on the deep dive.
Always a pleasure.
And thank you for listening. Next time you type a text message, maybe give a little nod of respect to the algorithm figuring out where your spaces really belong. See you next time.